Okay, we're back. All right, now let's squeeze all the way through here. I fixed the problem. It'll be transparent to you all, but I put the skydiver can dip it until he or she deploys a pit. No, that's not true. All right, so anyway, slowed down because which put a tremendous drag on his free fall. Yeah, I think I'd go with that one. Okay, now let's look at question 16. All right, let's look at question 16, pre-lab 16. What did I say here? 1357.6. Wow, that's pretty precise. 1,357.6 kilometers per hour. Let's figure out how many miles per hour that is. Okay. So there is 1.6 kilometers so basically what you do is you go 1 mile, this would be times 1 mile divided by 1.6 kilometers. All right, so that gets rid of my kilometers, and that'll give me my miles per hour. So if I just take this divided by 1.6, or maybe 1.609, either one of those will work, and you will get what it is in miles per hour. All right. The answer above is greater than the speed of sound. Yes, it is. 660 miles an hour, ballpark, is speed of sound. It's going a little bit faster than that. A solid, okay, so now we're going to talk about rotations, all right? For the next, okay, a solid disc has the same mass as a hoop. Which one is easier to spin? That was the whole point of this one slide right here, okay? Where I think I showed you, okay, solid disc, and this is for a hoop. This would be for a hoop type thing. So this is mr squared, and this is 1/2 mr squared. So which one would be easier to spin? If we put all the mass right here on this end right here and tried to spin it, or if we distribute the mass more evenly, put a axis through it, and then spin it. This is 1/2. This is 1, which is smaller. There you go. All right. It's tricky. I mean, this stuff's not easy. Okay, rigid bodies for an object with only rotation. All particles of the object have the same translational velocity. You don't even know what that means. That's going lengthways. Angular velocity. Hey, now you're talking. So I just tell you. Oh, okay. So, all right. Solid disk has a radius of 0.1 meters and a mass of 1.5. Calculate the moment of inertia of the solid disk. All right, so let's look at problem 20. This was 16. Let's look at problem 20. All right, so problem 20 says I've got a radius, or was it diameter? The radius, okay. Got to be careful, Diameter of 0.1 meters, gosh dang it, and a mass of 1.5 kilograms. We want to find its moment of inertia. And the mass is equal to 1.5 kilograms. Okay, so its moment of inertia, I, is equal to 1/2 mr squared. Okay, so you got 0.5 times 1.5 times, right, that's the way you do that, all right? And then a smaller disk has this radius. What's the moment of inertia of both of these disks combined? And this is kind of like the Dr. Dre commercial. This is why I showed that to you. So anyway, and I'm just getting you used to calculating the moments of inertia because you're going to have to do that with your lab, which I will make that movie on Monday. All right. Okay. So now the first disk is spinning at 33 RPMs. Okay, before that's that omega. All right, it's placed on. Now the second disk is placed on top of it. Will the two disks spinning together be slowing down, spinning slower than 33 RPMs, spinning faster? At this point in the spin, I don't give a rat's ass. All right? Or not enough information given. You can figure that out. Now, some advanced stuff for my lab rats. All right, so here we go. And this is the end of the pre-lab lectures. All right? This is the very end. So here's what we're going to do. We've got, I'll help you figure this out. So we're going to figure out, here's how you do this. I think in problem 20, you figured out I of the big disk, right? So what problem is this? Question 23. Okay, so this is problem 23. I, big disk. And you've figured that out. So we'll call that IBD. All right, then we've got I of the small disk. Do the same calculation just with different radius, different mass. Will equal I of the small disk. Okay, so you've got I of the BD times 33.33 is equal to I of the BD plus I of the small disk. So you add those two together times omega. And this is what you're trying to find. So you have a number here times this number, and then you divide it by that number. So omega final, what they're spinning, will look like this. I of the BD, which you calculated before, times 33.33, divided by, and you can go ahead and just add those before you put that in. Okay? And then that's the way you do it. And that's a physics 240 problem, 210 problem. I mean, I kind of walked the dog for you, but still. You guys are animals. You're beasts. You can do this. All right. That is the pre-lab. I know it's long, but there's a lot of stuff involved here. The actual lab itself is pretty simple, and we'll talk about that on Monday. So enjoy this part. It'll be due Friday the 29th.